maximizing production from the existing well assets. Current production projected OPEX versus CAPEX trends show an increasing demand for maximizing production from existing and maturing wells. These macro drivers have steered development efforts in key segments, including acid stimulation and water and gas conformance. Today, our group of speakers will share those development efforts with us. So let me introduce them. Our first speaker will be Paul Hussein. Paul is the director of the Schlumberger Stimulation business line under Reservoir Performance Division. The stimulation business line is responsible for hydraulic fracturing, acid stimulation, sand control, fluids and pumping, and as well as Schlumberger stimulation vessels. Our second speaker will be Christine Anderson. Christine has been the Stimulation Surface Equipment Product Manager for Schlumberger since September 2020. Previously, she was Operation Stimulation Manager in the Permian, and she is responsible for stimulation, technology management, and deployment globally. Our last speaker will be Philippe Nkababian. Philippe is a Stimulation and Conformance Control Advisor for Schlumberger. He is currently in the Middle East and North Africa stimulation domain, based in Abu Dhabi, and he is responsible for the development of stimulation technologies to address completions and production challenges from our MENA operators. So now let's move to the agenda of what we're gonna be covering today. So first, Paul will start with the introduction of the matrix stimulation and conformance, basically covering opportunities and challenges. He will be followed by Christine, who will be taking us through the technical solutions. And then we will be closing with Philippe presenting some case studies and wrapping up the presentation. Well, let's start. So Paul, handing over to you.
Thank you very much, Pedro. And again, good morning, good day, and good evening, everyone. Next slide, please, Pedro. So I'd like to first talk about a little bit of the macro information that demonstrates why we believe there's a good opportunity for both matrix stimulation and water conformance to extend the life of your producing assets. The chart on the left, based on industry data, shows how the industry will meet the increasing demand for hydrocarbons through the next decade. In 2021, we see that 63% of production will come from either late life or midlife producing wells. These are wells that are actually, in their midlife being between 25 and 75% of their production life, and late life being greater than 75%. However, as the industry transitions, we do expect a slowdown in new mega projects and more exploration activity, leading to an increasing proportion of productivity coming from so-called mid and late life wells. And you can see that by 2030, as much as 78% of production will come from that horizon. The chart on the right shows, however, that despite all of the growth that we have seen in the unconventional plays in the so-called graded area of the reservoir types, clastic and carbonate reservoirs will continue to contribute the majority of the production landscape, more than 70%. It is in these reservoirs that we need stimulation either from acidizing or fracturing, but as they are typically conventional, we expect to see more than just fracturing. Next slide, please, Pedro. And so with the aging profile of the producing assets, what are some of the challenges that we expect to see? Of course, there is production decline. And typically, as wells mature, they typically have higher influx of fluids with water cut increasing. You typically get skin increasing, particularly in sandstones, as you have the migration of particulates and fines towards the near wellbore area. With lower production, of course, you get more complex economics in making the fields productive. Another impacting phenomena is that of differential depletion, where you typically see more rapid depletion of your high permeability zones. And in fact, when you get stimulation that is typically uneven, the better stimulation zones deplete faster. This leads to the phenomena of crossflow, where a producing zone, instead of getting to surface, may in fact enter a zone higher up the wellbore, drastically affecting total well production. And when you attempt to stimulate a well that has a depleted zone, typically it is the lower pressure or depleted zone that gets all the treatment fluid, negating the effect or the intent to stimulate the other areas of the wellbore. And last but not least, we are faced with conformance issues, either water breakthrough or gas breakthrough, both affecting the production potential of the well. Moving away from a reservoir base, if you just look on the well cases, you typically see, of course, increasing problems with well integrity. You get tubular corrosion with time, especially when you have more water production, and you could suffer long-term cement deterioration, causing a breakdown in integrity and lack of isolation between zones. Accessibility and intervention is also an increasing problem with the age of wells and maturing fields and assets. Quite often, when designing the original wells, the completion engineers fail to predict the type of interventions that would be needed over the life of the well. And it becomes quite complex to intervene in the late life. Things such as dual string completions, the wrong or small ID type wells, or sometimes very complex completions in the open hole. There's also the added difficulty of the cost and complexity of acquiring data. And we will talk later in the presentation, the importance of capturing data to be able to diagnose the problems of late well production challenges. And last but not least, as many of you probably know, when you have fissures or intervention challenges in wells, these actually complicate significantly our ability to intervene. So let's talk a little bit about the details of each of these topics. So when we talk about carbonate wells, almost 90% of these wells are actually stimulated using acid stimulation. And this is quite simple because carbonate rocks react with hydrochloric acid. However, despite a large number of wells being stimulated using acid stimulation, we know from industry literature that as much as 60% of these designs are not, these stimulation treatments are not designed or engineered. Another 20% may have some type of design, but they're not optimized. And a small 10% of the wells are actually designed with a robust engineered approach to the stimulation treatment. But what is the reason I'm mentioning this? It is because we know from industry literature that when you actually do a good stimulation design, you can get as much as 80% production increase on a carbonate well. Whereas when you do no design, the increase is typically between 10 and 20%. So essentially, good designs give good results. So what's actually a good design from an acid stimulation perspective in a carbonate reservoir? First, you need to pay attention to diversion, because most wells, of course, have differences in permeability along the wellbore or along the lateral. You need to, of course, control the reactivity so that the acid generates a long wormhole and is not spent uncontrollably in the close or the near wellbore region. And you need to design your acid correctly so that there are no incompatibilities between your treatment fluid and your formation fluid that may lead to sludges or other materials that can plug the near wellbore area. Christine will talk later on some of the techniques to use to get good optimized acid stimulation treatments. Next slide, please, Pedro. When we move to sandstone acidizing, it's a different picture. Of the total potential candidates, which are in the hundreds of thousands of wells worldwide, we know from industry literature that a mere 20% are actually stimulated in sandstone reservoirs. And why? It's because of the 20%, almost 60% of it, or 12% of the total basket, actually do not give good results. In fact, many stimulation treatments in sandstones actually damage the well and result in poorer post-stimulation treatment. No wonder customers don't want to do stimulation treatments in sandstones. And a very small 8% of the well basket actually result in an increase in productivity. And what are the reasons for failures in sandstone acidizing? First, as mentioned before, inadequate diagnostics and fluid selection. It's very important to know what are the damage mechanisms in a sandstone well before attempting the stimulation. When the fluids are incorrectly selected, you potentially can get complex secondary and tertiary chemical reactions. And these can introduce a number of additional damaging mechanisms, such as clay swelling and pore blockage, as the picture on the bottom attempts to show, the generation of insoluble precipitates, or sludge and emulsion formation that plugs the wellbore area, the near wellbore area. Another challenge, very similar to that of carbonate acidizing, is about ineffective reservoir coverage, good designs needing a plan for good diversion. And last but not least, a lot of you practitioners of stimulation jobs know that sandstone acidizing treatments are quite complex in the current way we approach it, with multiple stages, including pre-flushes, mutual solvents, brines, then the main treatment, and multiple post-flushes and spacers as we complete the treatment. Such complexity is prone to human error, and many a sandstone acidizing job has failed due to surface and execution problems. Next slide, Pedro. And when we move on to the challenge of water production, the chart below from an SPE source shows that across the globe, we have a very large amount of water producing in all the key operating areas. In fact, it's currently estimated that more than 250 million barrels per day of water is produced across all environments. That's between 3 and 5 barrels of water, depending on which region you consider, for every barrel of oil produced. In fact, in North America, in US land, almost 55 million barrels per day of water is produced. That's a whopping 20 billion barrels per year. And this inherently introduces a lot of problems and complexity. First, there's the operational challenge, which is around handling that water and disposal. And the reuse of produced water is a very regulated industry. It, of course, results in reduced recovery, because in many cases, we are injecting water into reservoirs to get better sweep efficiency. And if you get early breakthrough, it does not achieve the objective of sweep, and ultimately reduces hydrocarbon production and ultimate recovery. But there's another problem introduced due to abnormal water production, and that is around well integrity, because it causes accelerated corrosion of the tubulars, as well as scale and other deposits. So quite a serious problem indeed. Next slide, Pedro. And what are the ways that we address it? The first is you need to get correct problem diagnosis. And the graphs below show all the different reasons and sources of high water production in a well. Anything from integrity issues, such as holes in the casing or flow behind pipe, to more reservoir issues, such as fissures and coning and gravity segregated layers. So understanding the water path is critical. We need to verify that isolation of a water producing zone will not cause production loss, and confirm that whatever solution we put in place will actually last the long term, and pay specific attention to selecting the appropriate remediation technique. From a design perspective, we must ensure that we can actually target and isolate the treatment area, and pay particular attention to selecting the correct fluids and getting the adequate placement. So much so we know, and we're open to say, that many solutions that are proposed can actually fail if not correctly designed, such as when you have casing patches if the issue is poor cement behind casing, or when you try to use relative permeability modifiers if the problem is two-phase flow. And we need to recognize that it's a complex issue, and some solutions may not be able to deploy it at all in certain completion types, and hence the importance of planning your completion for the long-term full life of the producing well, such as when you try to treat open holes through slotted liners, which is very, very difficult to achieve adequate placement and coverage, or where you have small restrictions that can prevent the use of inflatable packers for zonal isolation. So I explained a bit the opportunity and the challenges in each of the spaces of carbonate, sandstone, and water production. Next slide, please. I'll now pass you on to Christine, who is going to now explain some of the technical solutions to address those challenges that I just mentioned. Thank you. On to you, Christine.
Thanks, Paul. Good morning, good afternoon, and good evening, everyone. As Paul mentioned, I'll be walking through the next part of the presentation, which is our technical solutions. So as we move on to the slide showing, when we look at the design and mature wells for matrix stimulation and conformance control, we ask the same high-level questions. do we understand the problem? Can we fix the problem? And finally, is it worth it? Ultimately, for any intervention, the incremental production and added recoverable reserves needs to justify the expenditure. For matrix stimulation, we need to understand which zones production can be improved from in order to determine where the stimulation or re-stimulation needs to occur. Also, we need to understand if the decline in production is a result of wellbore damage or a result of the well's depletion. If the decline is a result of damage, what the damage is and where it is located is needed to determine the ideal solution. For matrix stimulation, as we move into the next step, we evaluate if we can fix the problem. In order to fix the problem, we first need to diagnose if we can get the acid to the target zones, or will it be lost to a thief zone? If loss of fluid to a thief zone is a concern, we can utilize a diverter solution. Another way to address the problem is to evaluate if we can minimize workover frequency by combining the matrix treatment with an inhibitor that will stay within the formation and delay the onset of repeat problems. When we move on to designing conformance control, we ask the same questions as in matrix. As Paul mentioned, most reservoirs will produce unwanted water during their life cycle. Managing high unwanted water can be very costly and may have detrimental effect on hydrocarbon production. We start with, do we understand the problem? Do we know where the water is coming from? Is it possible to isolate the water zone without impacting the oil production negatively? We then move on to how can we fix the problem? In order to do this, we need to evaluate if we are able to isolate the water without damaging the rest of the formation, and will the isolation of water provide long-term benefits? For long-term benefits, the goal is to determine if the treatment will last or will water find a way around the treatment. Finally, after we review the questions of do we understand the problem and can we fix the problem, we loop back to the last question. Is it worth it? An effective treatment will result in incremental production and added recoverable reserves that justify the expenditure. As we move on to the next slide, we'll discuss some of our new acidizing and fluid and diverter technology. In order to address the challenges and ensure the treatment is worth it from the assessment and design from the previous slide, new acid fluid and diversion technology has been developed. For sandstone acids, we're looking to restore the original reservoir permeability through the dissolution of the damage, blocking the pore throats and the formation matrix. We want to remove the fines to prevent the construction and pressure drop at the reservoir. Traditional mud acid tends to be spent and reprecipitates or can have a chemical reaction that forms immediate precipitates. Advanced sandstone acids have chemical formulas to prevent this precipitation of particles. Sandstone acids, such as clay acids, can use slow release of hydrofluoric acid. Schlumberger's one-step is an advanced simplified sandstone stimulation system using only one fluid stage. One-step is a chelant-based sandstone acid, which uses chelation or inhibition of ions that could precipitate, thereby minimizing the risk of secondary and tertiary precipitates. As the fluid solution is a single-stage acid, it has a lower risk with a higher operational efficiency. The one-step system promotes the stimulation of wells that were previously bypassed because of a fear of potential damage from conventional treatments. This is successful to stimulation in some specific reservoirs with challenging lithology. Schlumberger has recently also developed a more robust version of the single-stage sandstone acid system, continuing to lower the risk, increase operational efficiency, and have a smaller operational footprint. The challenges for carbonate type stimulation are different than that of sandstone. The main challenge is penetration. We want to bypass the damage by creating wormholes to better contact deeper into the reservoir. When using straight hydrochloric acid, it reacts so fast that it just dissolves the very near wellbore and does not have the deep penetration and contact into the reservoir. In order to penetrate further into the wellbore, we need to slow down the reaction and this is done by emulsified or retarded acid formulations. Emulsified and retarded acids allow for lower pore volume to break through, even at low rates, by slowing down the reaction. This allows for the deeper wormholes. Emulsified acids typically have operational challenges with batch mixing of chemicals to develop the emulsification though. Schlumberger utilizes a single-phase retarded acid system, open path reach, which simplifies these operational challenges while still achieving the contact with the reservoir. Open path reach can be mixed on the fly, while emulsified acid systems cannot. In addition to open path reach being easier to pump, it also has a lower friction pressure than emulsified acids, further simplifying surface operations. In a carbonate, the permeability depends on the natural fractures, fissures, and the formation is also typically heterogeneous. When treating a well with carbonate lithology, there can be varied permeability between various zones. Fluid follows the path of least resistance. So in the case of varied permeability, the treatment potentially will flow into one zone, leaving the others untreated. This creates the need for a chemical diverter to temporarily plug the near wellbore area, reducing the permeability to allow fluid to flow to another zone. This temporary diversion is completed with Schlumberger's open path sequence portfolio, which utilizes a blend of degradable fiber and particulates. For a divider selection, different particular sizes are required for different applications. Larger size particulates are needed for wide faults or a hydraulic fracture with natural fissures, fractures, or a porous matrix. But smaller size particles will be required if the diverter is pumping with coiled tubing placement or placement through screens or a gravel pack. There is also a temperature application for the degradation of the particles as well. As we move on to the next slide, we'll begin discussing matrix stimulation modeling. Schlumberger's kinetics matrix stimulation design software integrates reservoir petrophysical and treatment fluid chemical data to optimize matrix treatments. With carbonate acidizing, we are dissolving rock and considering the permeability against different zones, thickness of zones, lithology, temperature, and optimum rate you can pump to get the ideal wormhole while still minimizing the fluid volume used. Schlumberger modeling software, Kinetics Matrix, utilizes these parameters to optimize the design for carbonate acidizing by modeling the volumes, skin, and performance you will achieve by sensitizing on various parameters. It creates acidizing models for limestone and dolomite at well scale and has wormholing initiation and propagation models. Verification of modeling software was completed with laboratory characterization with cores and scale up to field conditions. Sandstone acidizing also uses Kinetics Matrix for stimulation modeling software to calculate geochemical simulations at well scale. Reactions resultant from primary, secondary, and tertiary reaction are calculated, as well as the ability to determine precipitate materials that can be generated and determine if the impact is damaging. Verification of modeling software for sandstone acidizing modeling was completed with laboratory calibration and scaled up to field conditions. Finally, placement models using mechanical or chemical diversion models can be simulated as well as multiple wellbore completions. Distributed temperature sensing, or DTS, data can be integrated into the model as well. As we move on to talk about our conformance control solutions now. Success of the water shutoff is dependent on proper identification of where the water is coming from. Water shutoff solutions for near wellbore problems, such as casing or tubing leaks or flow behind the casing, and fractures and faults, such as between an injector and a producer, typically rely on mechanical or fluids and chemical solutions to address the water conformance control. When we look at fluids and chemical solutions, there are some legacy fluid systems that can still be utilized, such as polyacrylamide and inorganic gels. Examples of these are Schlumberger's Meraseal, OrganoSeal, and ZoneLock, which are used to plug matrix or natural fissure network. There are also conventional or microfine cement squeeze slurries, such as Squeezecrete, which is used to plug perforations or repair cement integrity issues. There are also relative permeability modifiers, or RPM, to selectively isolate water layers, such as what ZoneTrol does. There's also a new family of products currently being validated. One of these solutions is a water reactive system, which uses microfine cement or gel particles suspended in a non-aqueous fluid. Schlumberger's portfolio for water reactive systems is Water Seeker. The Water Seeker system, composed of micro cement suspended in miscible solvents, rapidly hydrates and sets only when in contact with water. But when the slurry comes in contact with oil, it remains liquid and flows back up after treatment. This leaves the oil-producing zones undamaged. There are also foam gel systems, such as FoamSeal for gas shutoff, and nanoparticulate systems, such as All-Seal particulate gel for matrix near wellbore plugging, and annular chemical packer systems for open hole completions, such as slotted liners. Mechanical solutions are still an option if the completion allows. These include expandable casing patch or inflatable packers. As we move on to our next slide, we'll discuss downhole measurements. Downhole understanding is critical to the success of simulation and conformance treatments. Distributed temperature sensing, or DTS, can be used through derived flow or direct measurement. This is used to understand the differential injectivity between zones, flow behind the casing or liner, flow around annular packers and open hole completions, or diversion in fluid penetration monitoring. Additionally, bottom hole pressure can be used to identify excess, depletion, and status of the inflatable packer. Finally, depth correlation of gamma ray and casing color locator can be used for accurate packer or guns positioning. I'll now hand over to Philippe to cover some recent case studies.
Thank you, Christine. The next few slides will focus on two published case studies I co-authored in the past few years. I chose them because they illustrate how new chemistries, downhole monitoring, and design workflows can be used to improve stimulation and performance operation. Next. The first paper is related to carbonate matrix stimulation in a long open hole horizontal well. Such stimulation are inherently difficult as carbonate permeability and isotropy often lead to substandard stimulation in the tighter intervals. Now, to address this concern, we developed a two-step approach as part of this work. The first phase focused on first identifying the tight interval with a distributed temperature survey, and second, pinpoint stimulation of these intervals to increase their injectivity prior to the bullhead treatment. The second phase was the high-rate bullhead treatment based on a new single-phase retarded acid, namely open path rich. This acid was selected because of its ability to create deep wormholes at low injectivity rate and its lower viscosity when compared with emulsified acid. For diversion, both a new degradable fiber and particulate diverter, namely open path sequence, and a viscoelastic diverting acid were mobilized to the well site for thief zone or matrix diversion. Next. The first distributed temperature survey on the left was conducted prior to the coiled tubing stimulation, and it clearly indicates the unexpected presence of a thief zone in the middle of the horizontal section where the temperature drops drastically. Had we bullheaded the main treatment blindly without identifying that problem, most of it would have gone down this thief zone, leaving most of the well unstimulated. After realizing this new challenge, the acid jetting procedure was modified to include the bullheading of a degradable diverter peel down the coil tubing annulus. This peel was added to bridge the thief zone and further increase the chance of injecting the acid into the tighter intervals in the lower part of the well. A post-jetting distributed temperature survey was done on the right, and it indicated that the thief zone was still predominant, but it also showed that the jetted lower section experienced a cool down consistent with increased injectivity. Next slide. Based on the post-jetting DTS, the main acid job program was modified to include a larger degradable diverter peel pumped ahead of the treatment. The purpose of this peel was to divert part of the treatment away from the thief zone and into the tight intervals. The 630 barrels main acid treatment was then bullheaded at 12 to 15 barrels per minute with alternating stage of retarded acid and viscoelastic diverting acid. After the treatment, coil tubing was run one more time in the well to perform a post-stimulation DTS. The injectivity showed that the index had been multiplied by 5. And although the thief zone still proved to dominate the wellbore flow, the temperature behavior across the tight intervals indicated that a significant fraction of the acid had entered and stimulated the lower intervals. Without the ability to understand where acid went right from the beginning of the treatment with the initial DTS, we would have been completely blind to the permeability and isotropy, the extreme permeability and isotropy of the well. This challenge is quite common in carbonate wells and even more common in mature wells that were previously stimulated with substandard diversion, in the case where a thief zone is going to be overstimulated, leaving most of the rest of the well unstimulated. The ability to understand fluid dynamics and address them with the right type of acid and the right diversion design in that two-step design workflow was critical to the proper stimulation of this well. Next slide. The next case study is related to a conformance treatment we performed in a depleted mature oil well producing from fractured carbonate reservoir. The well was completed with a 4.5-inch open hole completion consisting of 16 swell packers and 18 ICDs. It produced at around 90% water cut, with most of the water coming from the two lower ICDs at the top. The conformance treatment combined two distinct chemistries. First, a cross-linked polyacrylamide system, namely organosil R, that would be used to plug the fracture network to a depth of 5 to 7 feet to keep the water away from the well and prevent early breakthrough. A nanoparticulate gel, namely all-seal particulate gel, would then be combined with the polyacrylamide gel to minimize the matrix leak-off and keep most of the organosil R in the fracture network. The treatment was designed to be placed through an inflatable retainer that would be left in the hole with cement on top to ensure wellbore isolation. The inflatable option was the only option available due to the wide tool ID restriction. To ensure proper packer placement, controlled inflation, and accurate top of cement, it was decided to use instrumented coil tubing to measure downhole parameters in real time and ensure proper coil tubing depth correlation. Next slide. So here is an illustration of the operational sequence. The first step was the setting of the inflatable packer 20 foot above the second ICD using CCL depth correlation. After controlled inflation, the bottom hole pressure was measured to confirm the adequate setting of the back pressure valve we had in the BHA to control the fluid flow and prevent over displacement in this subhydrostatic well. Static temperature was also measured to ensure the gel would perform as designed. It is not uncommon to find discrepancies between the expected and actual bottom hole temperature. Without a direct measurement, temperature discrepancies can lead to gel setting prematurely or not setting at all. An injectivity test was also conducted to confirm sufficient injectivity was there to squeeze the fluid, and that the measurement of rate and pressure were consistent with the swellable packer integrity. A leak in the swellable packer would have resulted in the gel bypassing the formation and going into the next compartment. Without a bottom hole measurement, the integrity of the swellable packer, or in some case perforated completion, the integrity of the cement behind the liner can sometimes be doubtful and could lead, if defective, to gel placed out of zone and a resulting failure of the treatment. Can you click? Thank you. After the well integrity and bottom hole data were confirmed, the gel was mixed and squeezed into the lower compartment and surrounding fracture network. The gauge tubing was then disconnected from the inflatable packer and a cement plug was placed on top of it. Then the top of cement was dressed to fall below the third ICD and allow for its opening. Next slide. 308 barrels of polyacrylamide and nanoparticulated gel were squeezed in the lower compartment in the fractured formation. In the wellbore, the inflatable packer was left in the hole with 52 feet of cement on top. After the treatment, the well water cut went from 85 to 90% down to 50 to 55%. The water production dropped from 1,300 to 400 barrels per day, while the oil production increased from 150 to 350 barrels per day. Not only were these results better than expected, but they were sustainable in time. The graph on the right shows how production remained relatively stable over a period of 9 months, during which the water cut only slightly increased over time. This case study was a clear demonstration that the right combination of chemistries, placement method, and real-time downhole measurement can lead to significant reduction in water production, even in a mature depleted well with uncertain completion integrity. Next slide. In conclusions, the proportion of hydrocarbon production from oil wells and infill wells in mature field will continue increasing. The inherent challenges associated with completion integrity, depleted reservoir pressure, reservoir conditions, provide an opportunity for enhanced production via matrix stimulation or restimulation, as well as conformance treatment. In the last few years, new chemistries, placement method, downhole monitoring, and software modeling technologies were developed to address this opportunity in ways that can, in some cases, reduce both the operational footprint and the risk level. Now, beyond the chemical and mechanical solution, accurate diagnosis, downhole measurement, as well as advanced design workflow are still key to operational success. Understanding the challenge and what is happening during the operation can make the difference between success and failure. Altogether, Schlumberger's portfolio of advanced technical solution and design workflow can be leveraged to address the challenges you face in extending the life of your mature assets.